So this is Terrence Barkin. I'm the host of today's webinar on graphene and EMI shielding. I'm the executive director of the Graphene Council, and we're joined today by SP2 Carbon, who's going to present with Tim Nelson and Christian Oberleitner making the presentation today. For those of you who are not familiar with the Graphene Council, we are the largest and the oldest trade body for the graphene sector, representing all of the major graphene manufacturers and end users worldwide, connecting more than 30,000 material scientists from both the academic and commercial realms. We also work with industry vertical organizations to help spread the word about using graphene and encouraging commercial adoption of the material. As you see here, this is a representation of some of our member organizations, which include the University of Manchester, as well as other leading institutions. The Graphene Council provides expert advisory services and information on all things graphene, including the Graphene Report, more than 500 pages, covering graphene production methods, characterization techniques, commercial forms of the material, and market intelligence. And with that, Tim, I'm going to invite you to go ahead and get started. If you want to bring up your screen and introduce SP2 Carbon and yourselves for today's presentation.
Thank you, Terrence. Yes, welcome everybody. We really appreciate you joining us today. And I'm going to go ahead and click to the next screen here to show another picture of Christian and I here. But just real quickly, I realize everybody's at all different time zones, so just welcome, good morning, good afternoon, and good evening. Firstly, I'm Tim Nelson. I'm the marketing manager for SP2 Carbon, and the other presenter is Christian Oberleitner, and he is the CEO of our European operations. So we are looking forward to talking to you. So I'm going to start off with a couple of slides, and then I'll hand it off to Christian, and then I'll be back with you a little bit later. So firstly, I'll just go through the overview of our presentation. I'm going to introduce our SP2 Carbon team. We're going to talk about the value, the SP2 graphene value, and an overview that includes our SP2 Carbon mission. We're going to talk about some of the application opportunities. That includes SP2 Carbon technology that involves thermoset and thermoplastic composites. Then we're going to demonstrate some of these values that we're presenting, the SP2 Carbon values, with some technical data and show you our technology in more detail. And then finally, we'll have a summary. And then after the summary, we'll have a question and answer period to be able to answer any questions that you guys have. So again, thank you for joining us today. And let me introduce our company and your global SP2 Carbon global team. All right, thank you. And this, Christian, you can go ahead.
Good morning, good afternoon, good evening as well. Yes, SP2 Carbon. We do have a global network in our setup. So we're represented in China, Taiwan, US, and Europe. We do have a global reach. And we include in our technology and in our portfolio also graphene production, global sales and marketing activities, but focusing on the composite industry. This goes without saying, especially experienced people in the composite industry, it's all about technical support and technical service. So we cover all the composite applications on, unsettled polyester, vinyl ester, epoxy, polyurethane, phenolics, but also, and that's quite interesting, we do include thermoplastics. And when we talk thermoplastic, we talk about glass reinforced thermoplastic, and out of this technology, obviously, there's also application for coatings, including water-based system, etc. Quick one, the founder, patent holder, and inventor of the core of our technology is Randy Poole. Randy and I, we both have been working at Reichhold. So Randy is a Taiwanese origin, and together we have 30 plus years in the composite industry. We both worked at the Reichhold resin company, producing resin and also technical service for the resin in all the application, from closed mold to open mold, even without reinforcement. And we both had the experience and the pleasure also to work in the glass industry on different fields, but highly focused on Randy being, Asia and North America, and myself focusing on Europe and crossing over to North America. Further, we have Alex Chang, he's our COO. We have a technical service manager, Norman Seng. He's a former Michaelman expert, and then we have just two more, our office manager here and our COO in SP2 Carbon Europe. Please, let's move into the technology. So graphene, I'm going to be relatively brief. The majority of the people on the phone and on the call do know what graphene is. Our mission, however, is basically to make sure that any graphene, not the ones that we produce, so SP2 Carbon works with all the graphene suppliers globally, and we have tested about 90 different graphene types that we consider industrial or industry ready. And we have seen that although graphene has all the beautiful potential, and it certainly has, the translation into the composite industry, and especially on the thermoplastic thermoset side, due to the processing, due to the mechanical environment that graphene is exposed, has some challenges in terms of consistently delivering those performance attributes. So we have seen that there's some damage, there's some improvement or restoration needed for the graphene to withstand the processes in the composite industry. And that's exactly where we are offering our services. And we have developed solutions, additive, to compensate and restore those graphene. And we're trying to bridge from the graphene manufacturer to help make sure that the graphene is ending up in the composite industry, especially by the compounder and the molders, to perform and bring that performance to the final part. Where do we focus? We focus on EMI shielding applications. Some of the targets that we've seen, there's a significant need when it comes to storage tanks and electronics, eliminating ESD, increasing conductivity. So we're also focusing not only on electrical, but we do have some thermal conductivity results coming up soon. So there will be another patent being issued relatively soon. And by the way, all these technologies are US patent pending, and we're in the process of finalizing this. So we're in the final stage there. And at the end of the day, it's about fine-tuning the dielectric constant values in or at the end of the composite application. Here's a slide you may have seen, and Terence may have shared this as well. I just want to touch a little bit about, you have single layer graphene, which is basically the high end of graphene available. There's a lot of patent work also within the Graphene Council on optimizing and bringing that technology of producing single layer graphene into mass production. So there's a lot of activities. Then there is a whole segment of single and multi-layer graphene. I think that's where, coming to the composite world, where it really starts making sense, because there's always not only the performance side to be evaluated, but also the cost side of it. So single layer graphene is relatively still expensive, mainly driven from the production technologies available. Single layer, and then we have bulk. And you see in this, it's a beautiful overview of potentials. We focus obviously on the top right, which is the red circle, on the composite industry, but the composite in itself is touching energy, is touching corrosion resistance, it's touching medical coating application, batteries as well, but within batteries, and we have two further slides on batteries, we're differentiating between the inside world of the battery, which comes back to single layer, and the composite more being in the surrounding area, temperature management, and again, conductivity. So I just wanted to show that there's a significant field of opportunities, and we do focus on the single multi-layer crossing over to the graphite, where there's somewhere between 50 and 100 layers. There's a border between graphite and graphene that we see viable to be used in the composite industry.
Okay, thank you, Christian. So I'm just going to touch a little bit on some of these application opportunities. And as Christian mentioned, we're going to be talking about electromagnetic compatibility. So there's many standards that are out there for EMC, and unintended electromagnetic energy in any electronic device can cause issues in the environment within itself or within other electronic components that might be nearby. So the shielding is the practice of surrounding the electronic device with a conductive material that curbs that flow of electromagnetic emissions. So this EMI electromagnetic interference, if you can curb it and prevent it from interfering, that's the goal, and that's where we're finding our value fit with these applications. All electronic devices share this electromagnetic spectrum, And when in close proximity, they will interfere with each other's performance. The electromagnetic wave will radiate, and of course, it will then disrupt any electronics that are around it within a certain range. So the emissions and immunity guidelines have been set by different regulating bodies such as ISO and some other bodies out there in the different industries, and we'll touch on those in some coming slides. But one of the other issues that we're always concerned about, of course, is electrostatic charge. And being conductive, having conductive composite, we could help dissipate any electronic charges that can create some damage also in the electronics. So one example we could touch on here with you guys is the electromagnetic fields in a radio frequency RF spectrum. They're part of the, they have a frequency, anywhere from 3 kilohertz up to 300 gigahertz. And these waves, they're used for transmitting signals, and but they could also interfere with other electronic radio waves. So electronics has become more and more sophisticated. There's more and more behind the scenes where you got components that are trying to create radio frequencies or other communication signals that can then interfere with each other. So, for example, in an automotive collision avoidance systems, they work at around 75 gigahertz. And so some of today's metal and graphite composites, they can suffer some degradation at around 18 gigahertz. And some of the degradation is due to some inherent challenges that are made when these components are manufactured. One of these challenges is skin effects. So in general, a skin effect is when currents will crowd into the uppermost layers of the conductor. And when that happens, the current's density increases and produces an increased voltage drop. And so shielding barriers placed in the path of the electromagnetic field, they can help be a shield and barrier, and they can help keep and what we do in our formulation is going to help prevent the skin effect altogether. So essentially that skin effect, if you can help dissipate it within the conductive material, you're going to eliminate one of the potential issues in the design of the components that you're using for electronics. So as the frequencies go higher, then of course wavelengths are shorter. And with that, if you have any gaps or anything that's in that shield, it's going to become a potential site for leakage. So, frequencies tend to go higher as we are developing more sophisticated electronics. And just lastly, I just wanted to show you here that EMI shielding market is expected to be 6.2 billion in 2021. So with a significant CAGR growth year to year. So we're really seeing some opportunities in this market space. So as a conductive composite, there is an ASTM test method for measuring the electromagnetic shielding effectiveness within a planar material. So this is one of the test methods and standards that are out there. And this provides a procedure for measuring the electromagnetic shielding effectiveness of a planar material. And so this is one thing that we can touch on a little bit later in our presentations as well. But this method it basically is valid for frequencies of 30 megahertz to 1.5 gigahertz. So an electromagnetic shielding effectiveness is the amount of EMI attenuation expressed in terms of decibels. So we'll show some test data a little bit later, specifically with our product, but in general, if you have a shielding effectiveness that's less than 10 decibels, that's not real appropriate shielding. If it's in the 10 to 30 decibel range, then it's starting to become more effective. And of course, typically you want to be above that 30 decibel range in order to have acceptable performance and shielding in most industrial and commercial applications. So typical conductive composites have about a 20 to 40 decibels shielding. But for a more conductive filler, you can get it up to 60 to 80 decibels. The downside, of course, is as in most applications, is if you're adding more filler to provide that conductivity, you're going to adversely affect the mechanical properties, and it's also increase the weight and potentially can increase the cost as well. So many times the conductive filler particles are not evenly distributed. That's the other issue, is when you're adding filler, they're not going to potentially line up properly as well, or if you're using some sort of a fiber, the fibers move in different directions, they can line up in different directions, so this can create issues. So, and then some of these fillers, as well as fibers, can then settle away from the surface. So many times when you're making a composite that's for conductive purposes, you have to treat the surface in order to get down to the conductive components that you've added. So anyways, the SP2 carbon additives will help provide a platform for getting intrinsically conductive polymers. And that's what we're going to be talking about in the remainder of our presentation. In the aerospace industry, of course, we have the FAA has aircraft electromagnetic compatibility certification standards that are out there. That SAE is an aerospace standards committee that creates some of these standards for the aircraft. Obviously, you can see from the photo, there's not only electromagnetic in the air around the aircraft, such as lightning in extreme cases, but also within the aircraft itself, because there's many electronic components and more electronic components inside. So this shielding shields against the high intensity radiated fields. The shielding is composed. Also, the aircraft has doors, windows, seams, and access panels, and so forth on the outside, antennas, and these all can help create interference points or points where there's no conductivity, where it can create some issues within the aircraft. For example, if a lightning hits the aircraft, then the electronics, the electronic conductivity is not going to be evenly distributed and could create some issues within the aircraft itself. So typically, aluminum has a conductivity around 35 megaseconds per meter, and at 1 megahertz, the skin depth is around 0.085 millimeters. So at these frequencies, any diffusion will for typical metal thickness can be negligible. Inherently, the conductive polymers intrinsically conductive polymers provide the ability to create systems for managing the lightning strikes and static discharge events that occur not only outside the airplane again, but within the airplane. So the composites industry is continuing to be significant in the aerospace market. Airplanes are more and more composed of composites. Many aircraft are now over 50% composite. So these are opportunities for having conductive materials within those composite components. Carbon fiber is about 105 at about 1 megahertz with skin depth of 1.5 to 5 millimeters. So that's just carbon fiber has been used in composites for quite a few years to help with conductivity. And what we're creating is a product that's going to help enhance any carbon fibers that are being used or any other conductive fillers as well. So let's go on to the next slide. So in the mass transit and rail applications, there's a continuing, again, a growing amount of composites that are being used. You can see an example in this train here. Obviously this train has to move fast. It needs to be light. Composites are lighter in most cases than metal. And so obviously more and more composites are being used in transportation vehicles as well. So the railroad and mass transit systems can experience EMI because, of course, they have emissions from train controls, propulsion systems, high voltage contact switching, and third rail shoes, train signaling and control systems. So a lot of electronic components, and many of these train systems are using magnetic systems in order to move fast as well on the rail lines. So again, graphite filled silicone is a common filler and component that's being used for cushioning and sealing and gap filling. ASTM standard C542 defines the required properties for these gaskets. These conductive fillers for shielding silicones is typically silver aluminum, but more and more is starting to be a nickel graphite, and mostly due to the cost of the silver aluminum fillers. So those are some of the fillers that are being used to help provide conductivity in the composites, whether it's thermoplastic or thermoset materials. And of course, nickel graphite and silver aluminum are metal and expensive and have some weight to them. So when you add more fillers, it gives you less flexibility as far as trying to meet some of the other standards that are out there for smoke and toxicity control. And so this is a list of just some of those standards, but basically, you know, as you can see in many instances, you know, when an unfortunate event happens, and if there's an accident with the vehicle, you know, if they don't want to have smoke and toxicity to be an issue, so they want the composites to try to self-extinguish if possible, if lit. And so having more flexibility in your formulations will be certainly a value when you're designing the composite components. So this is batteries, and I don't know if Christian, if you wanted to talk a little bit to this. I think
yes,
yep.
yes, please. Just a drop in on a different field. I think there's a lot of projects that have been on the market already globally, how to get into the batteries. So again, like I said at the very beginning, there's a graphene technology that really manages about the inside of a battery when it comes to charging elements or being in that field of making sure that graphene supports that charging. We are focusing from a composite side more about temperature management, so heat management, etc. So on the left side, you see basically the bottom floor of a battery in full aluminum, whether it's a Tesla or any other cars out there. There are two major challenges and the reason why they have aluminum or any metal in there. First of all, in case of accident, you need to provide safety in terms of fire and also mechanical performance with an accident, even there's with and without fire. And we all do know that, you know, there are significant challenges around batteries starting to burn. So that's why metal is going to be used. And the other piece is there's a whole technology about making sure your mileage out of a car is increased. How do you increase it? So today's technology is about the size of the battery for one, but at the same time recuperate any energy that you have. And during that recuperation process, there is a recharging of the battery, which helps you to add some additional mileages. But during that process, obviously you have an EMI shielding that would need, otherwise anybody sitting in the car would be exposed. So those two components could be potentially replaced by composites. I can see in the near future that I don't think there's going to be a full 100% replacement, but bits and pieces coming from composite with different technologies, whether it's SMC, pultrusion with a high glass content, giving you a lot of stability. But whenever there is a chance for composite replacing part of the metal, it's got to have conductivity performance in terms of EMI shielding. So it's a critical component. Obviously, it goes into the seals, the adhesives, the composite itself, and coatings. But this is an interesting application because we all know the growth rate of batteries being used not only as an electrical vehicle, but in general, that usage can be easily calculated, and it's coming.
And as in addition, I think Kristen mentioned this earlier, but medical devices also, of course, have gaskets and conductive materials that are needed within their components as well. There's shielding applications and conductive applications within the electronics. So obviously, we don't need to explain a little bit more about how critical that is, right, in the medical app field. But there's more and more medical devices being used with not only external to the body, but sometimes internal in the body as well. So this is another field where we see a lot of opportunity for conductive materials. Some of the other markets, of course, and we could go into it in more detail, but we'll just really mention here is that there's many applications in the telecommunication systems, information systems, and process measurement and control equipment. We can go on and on about the opportunities for conductive composites in the market space. Christian, were you going to talk to this slide, or did you want me to touch on it?
Absolutely. No,
Okay.
take place. So let's come back to why SP2. How can we help? How can we help the graphene producers, and how can we help bring that obviously known performance that we can all see in the lab in certain application into the final part? So this is all about what we have seen, including our own graphene that we produce. There's challenges. Sometimes it's work, so it's not a single solution that is ready and available out there without really looking into the whole supply chain when it comes from which graphite is being used as a precursor to the graphene production. How is it introduced into the resin? Which resin system? What's the curing? What's the technology being used to produce the composite part? And that's where our experience comes in. So at the end of the day, what we're doing is we're utilizing the experience of the technical service, the application, to make sure once we bring in the right amount, and obviously what we have seen, less is more. So it's not an overload if you don't get your conductivity levels as desired by just simply adding more graphene. You actually, it's a downside, it's a reverse effect. You're actually adding to the challenging problem of somehow destructing and losing some of the corner electrons and therefore losing conductivity. So the idea and the technology that we have developed is fine-tuning resin systems as an additive that can be used for the compounders in the industry within the standard equipment they already have in place. So I'm not going to repeat. It's again anti-static, EMI, EMF, and thermal conductivity in all the different resins technologies that we already have developed. Next slide, please.
Yep.
So at the end of the day, what it means, we have designed that ICP, intrinsically conductive polymers. So with our additive, we help to make for the specific application where it's needed, to allow to reduce weight, to bring in the composite part with the overall composite advantages of, again, weight saving, good mechanical performance when it comes to thermoset, also high temperature chemical performance, mechanical performance, as well as flame retardancy. So graphene also supports increased mechanical performance at the right dosage, and obviously introduces also a positive advantage whenever there's a fire in terms of toxicity, smoke, etc. So we have a patent pending technology where we end up designing a carrier system, introducing the right amount of graphene and other additives to restore some of the damaged graphene. We also have electronic boosters in the system to the lowest level needed to achieve the performance in the final product. So there's a certain milling process that takes place that we are considering. We also have very specific fine-tuned additives that support the processes that we undertake with graphene and other fillers to make sure there's an additive to be used. And then at the end of the day, bringing that into the final product. We also have developed this technology starting obviously with the experience that we have on the thermoset side, but we also expanded into water-based system, acrylics. We also see that phenolic, especially when it comes to train application, like Tim mentioned before, when it comes to flame, the combination of phenolic and graphene and their application is a significant advantage that we are really looking into and having very good results on moving into that technology. And again, it's all about the right balance of mixtures when it comes to graphene, additives, and also making sure that they function in the process along the way.
All right, so I'll show a bit of our test results. All right, so we've done quite a bit of extensive testing in the labs for quite a long time, and this, of course, is utilizing a lot of our experienced scientists that we have that have been involved in the industries for years. This shows an example of some resistivity and shielding on a unsaturated polyester neat casting. If you look at the first column, you could see there's no graphene or none of our additive in it, and you can see that the EMF source of 175, the shielding ends up being the same. There's in effect no shielding that is occurring in this neat casting. But while you can see the surface resistance is in ohms per square is greater than 10 to the 12th, which is basically at the line where the equipment can read and measure the surface resistance. So essentially, you've got a lot of surface resistance there, right? So you're not getting conductivity, you're not getting any shielding. If you look at the second column, there's 3% graphene added, and you can see, again, not much surface resistance. I mean, a lot of surface resistance, I'm sorry, not much conductivity. And again, you're starting to see some shielding, okay? You're starting to see a little bit dropping in that, from that EMF source, from 175 down to 99. If you go up to the 5% graphene level, it drops down to 81. Again, you're not still seeing on our equipment that we're using for measuring surface resistance, you're not seeing anything that's less than 10 to the 12. So go all the way up to 10% and then 20% graphene, you could start to see the surface resistance dropping. You see it so where we can measure it at 1.09 times 10 to the 12th. And then on the 20% level, actually you're seeing quite a significant drop. So from the 10% level to 20% level, you're starting to really kind of see where, okay, all of a sudden, the graphene is really contributing to adding conductivity to this neat casting, and you're seeing that it's actually doing absolute shielding as well. Whereas at the 10% level, it's still not. You're getting poor shielding, going from 175 down to 90, but at 20% level, you're seeing absolutely good shielding, and you're seeing good conductivity. So you finally get that graphene component into that composite material, the thermoset material, and you're starting to see the properties that we're looking for here. Now, if we step back a little bit and we go to where we're adding 3% graphene, we just add 0.5% of our SP2 carbon paste, which is our additive that's been specially formulated. It's been specially formulated to be compatible with unsaturated polyester. It's been so that's where our technology comes in. We have a formula that's going to be specifically formulated for the different resin systems out there. But you'll see where at that 3% level, much lower than 20, where originally we were seeing a high amount of surface resistance that couldn't even be measured on our equipment, is also now showing a improved conductivity and lower surface resistance of 7.48 times 10 to the 4th. And you can see absolute shielding in this application at that 3% graphene level with our additive. Now you go up to 5% graphene, again with the same amount of our paste in there, you start to see even a little bit better reduction in surface resistance. So this is just one application kind of showing you where the value of our product comes in, as far as if you could only imagine, once you're loading something up with 20% filler, right? How that will impact the mechanical properties, right? And also potentially the flame resistance and other flammability and other material properties within this component. If you can reduce that down to the 3 to 5% level, that's just going to give you a whole lot more flexibility in designing your formulation to get your composite where you want it to be in its performance, meets the standards that are out within those different industries. So this is just showing you a picture of some of those readings. The first slide, you could see, picture, you could see it's 1.02 times 10 to the 12th. It's showing an insulator, not good conductivity. You could see something now down to 5.91 times 10 to the 7th. So you're getting some conductivity there on this sample. And then finally, in the last slide, you'll see where you're getting some really good conductivity, similar to what we were seeing in the previous slide with our 0.5% level of our additive in that composite. So here's another instance of showing some technical data. We have a shielding effectiveness baseline that we're demonstrating here. This is an unsaturated polyester again, but this is a non-woven laminate. So it's got essentially fibers in there with also a gel coat on it. And so you can see a picture of it in this slide here, where we are measuring the shielding effectiveness. And this was something that we had talked about in a previous slide. So if you look here, you can see that if the decibel range, to really get, if you're below 10, you're really getting poor shielding. And you can see in this test, this is a actually got a lot of graphene in it, this laminate. And you can see that we're not, as we're going from 1 megahertz all the way up to 18 gigahertz, which is a pretty high level that we're seeing throughout that whole test run. We're getting well under 10 decibels. So not real good effective shielding that we're having in this example here. So now we take one that's got a little bit less, same laminate design, but a little bit less graphene in it. But at this time, we're adding that 0.5% of our SP2 carbon paste. And you can see in this graph and in this data in the table where we're now getting well above the 30 decibel range, and we're getting much better shielding in this example. So just by using our SP2 paste, we're helping that graphene to be able to do its job. This is where, Christian, you were going to talk about a little bit about the application.
In essence of time, because I think we really want to focus on Q&A, I'm just going to go through this a little bit quicker, and obviously we're available for any follow-up. Again, we have designed specifically to be compatible our paste systems to any different formulation, helping also on the technical surface in thermoset and thermoplastics. I just want to spend a few, 2 slides only, but also very quick. We're not only looking into how can we bring a paste into the resin system, we're also looking in, could we do anything on the reinforcement side? So like Tim said, today's usage, about 20%, 24% of the carbon fiber actually in use is used due to the conductivity, not necessarily because of the mechanical weight performance. Those are areas where we believe, and we have done some work, we are able to use, as an example, replacing a carbon surface wheel with an e-glass surface wheel, different cost position. We've developed a specific carbon additive, and you can see on that picture, this is where there's an impregnation phase into an industrial line of impregnating, in this case, 20, 50, 90 gram surface wheel. Next page, please. And we end up impregnating, curing it. And what you see here on the middle is basically we ended up with a graphene coated surface, e-glass surface veil that is allowing to give us conductivity. You see the measurement with our test setup, and you can also see that we have been significantly reducing and bringing conductivity to a surface veil, which then can be used into or replaced, in the field of any laminate being built up. So we have a balance between, we can bring in the graphene additive or high concentration of additive at the surface through the resin. We can bring it surface plus a surface wheel. We're also looking into reinforcement coatings just to make sure we have different places of areas in the composite, in the laminate, where we can start supporting the conductivity and the shielding where it's needed, which also has obviously a view on the cost as well. Next page. What we also would like to do is just very quickly, obviously we're not doing this alone. We are a global platform with about 40 people spread out in Asia, US, and in Europe. We have partners in terms of university. We have a university in Taiwan with a specific amount of capabilities around equipment, which is our partner. So we have even more technical data, and we would invite anybody on the call, whether you are a graphene producer, whether you are a formulator or somebody who has some challenges, to offer our solution, work with us, and also develop the data that is necessary to bring it back to the industry, to the final application where we're all going to be measured, talking about from a composite point of view versus a metal application. So I'm not going to go through this. This is a pretty intensive list of opportunities we have. Next slide, please. So in the summary, we are basically able to produce a real impact in supporting and improving composite with any graphene that is out there in the market, with a focus on different areas geographically. Conductivity is a topic, and I think the key word here for us is really customer service and technical service all the way down to the application. So around this Graphene Council, we're very happy to join. We're a new partner there. We invite anybody from the graphene industry. If you have challenges bringing it into a composite application, that we might be an additional tool in the toolbox to make it work for you. And again, we're customizing additive for the application, but we might also be able to customize to certain graphene groups of graphene and technologies out there, depending on the request. At the end of the day, however, what we are prioritizing are challenges where there's a market behind in terms of final part application. And I think that's where we do a lot in a theoretical analysis point of view, but at the end of the day, our goal is to go into the product market final application to deliver that value that we think graphene has in the final part. Okay, just a few last comments. So we talked about the partners. Please come and visit us. There's some finally physical face-to-face meetings available. We are presenting at the KMAC show. And we're also going to look forward together with the Graphene Council to have maybe certain further, after this general introduction, who is SP2 Carbon, what can we offer, going into further topics. So we can envision in the future to have a webinar focusing on thermosets only, thermoplastic, certain application, or when it comes to phenolic, I think there's a specific field that we would like to focus, or even epoxy, that we go through some of the findings that we're developing. And the last comment I would like to make is, again, as I mentioned, Randy Poo, our patent holder, is currently formulating another patent. I think there's a significant amount of opportunities around thermal conductivity, where we have seen tremendous results that we're looking forward to sharing with you when it's ready and available. Tim?
Yep. So we want to really thank everybody for joining us. So again, thank you. We're available for questions and answers at this point. And I'm sure there's a lot. I mean, we kind of showed some of the applications. We showed some of the test data, and I'm sure there's a lot of
Tim and Christian, thank you guys both. One of the first observations I think is important to note, though, is that as you presented it, you have this SP2 paste formulation that's used in combination with graphene that then goes into the host material. And I think that's kind of an important distinction. Can you talk about, the amount of graphene that's actually in the paste or that formulation? And the other question I have is about the replacement of metallics. So the typical materials used for EMI shielding are going to be metallic formulations. And are you using metallics in your paste, or is it purely non-metallic?
Okay. Allow me to take answer. So thank you for the question. I think that means we have an audience really knowing what they're talking about. So first of all, the graphene that we use in the paste is critical. We use all different graphenes we have screened. There are graphene, obviously, as we have seen and heard in different webinars, where it's coming from. There's a morphological geographical way how the plates are aligned. Inside the paste, we're trying to increase the graphene count to the maximum amount possible. Why do we do that? So we formulate the paste to have the highest loading possible with the right balance of additive, allowing for the customer to use as little as possible. And that varies basically on the chemistry that we have. So we have a different loading on a specifically designed paste for unsaturated polyester, vinyl ester, etc. We have a different loading on the vinyl ester. We have a different loading in phenolics. There's a lot of rheological chemistry, viscosity, also the milling process that we go through that allows us, but the target is to maximize the amount to reduce additive to the lowest level possible. Because obviously, with the exception of epoxy and phenolic, a carrier resin that is not the same resin will also provide a different mechanical properties, chemical resistance, because there's a reason why you use a phenolic resin or a specific Novolac type to begin with. If you replace that, the higher amount you use, the more you lose for the Novolac performance, as an example that you originally used. There is no metals in our formulation, so we're trying to replace metal. And I also saw one of the questions in Q&A. The idea was, like Tim mentioned, there is a blend out there for certain applications where metals are used today, where they take aluminum down, and there's a blend between graphite and graphene and nickel, but we're not. Graphene, at the end of the day, unless we're talking single layer, really high end, also comes with a cost. We're not even getting close in the composite to the final aluminum performance. And that's a goal, but we don't have to. We don't have to replace and compete and meet final metal performance. I think that's the overall challenge composite has, even without graphene and conductivity. Replacing metal doesn't mean in the composite world a one-to-one replacement. There's a lot you can do in design, etc. So it's really fine-tuning it to the application.
Thank you, Christian. Another question would be, do you see the market for your type of material more on coatings or actually making, parts, more substantive composite parts themselves as a shielding component, because a lot of shielding is done as a coating on top of another material, whether it's a sheath for cabling or cases for electronic components. And you mentioned before, just so I don't miss the thought, because aircraft are being more produced out of composites, they're losing the inherent protection they had when the skin of the aircraft was all metallic, right? So that's changed the dynamic. But do you see this as more coatings or more as parts?
I'll let Tim answer the aircraft part of the topic. At the end of the day, SP2 is providing a solution, whether it's the coating, the resin. That's why I also mentioned we're looking into the reinforcement side of it. I can see that there is a coating application market already existent, because it's also a little bit easier to put a coating on a product when it comes to shielding, right? Obviously, the coating in itself has advantages, flexible, you can add it, but it also has disadvantages, so it can also get destroyed relatively easy. What we have seen in certain composite parts, which also gets a coating, whether you call it a gel coat, a top coat or something, we can see that having a barrier coat or one coat of the first laminate behind any sort of coating, also providing conductive performance, helps in the overall resistance of the parts being exposed to whatever environment you're putting it in. So there's a safety guard behind. So at the end of the day, we're really focusing our efforts into the resin side, which is obviously the same chemistry as would be for the coating, right? So the same methodology will be used. But we have also seen that reducing the overall graphene amount in the resin could be achieved by having a graphene coated reinforcement, because it also gives you a three-dimensional laminate opportunity to already have a distribution of graphene throughout the laminate. Tim, maybe about your aircraft?
Yeah, so I think essentially the answer is yes to all of the, anything for coating and for composite, there's an opportunity, and it really opens up the playbook for all the manufacturers who are out there to try to look at different ways to resolve the issues that they have. Maybe, as Christian indicated, maybe it's a combination of a coating with the composite itself. But specific with aerospace, I could tell you just from personal experience, one of the issues that Boeing has been concerned with for years, back to the 80s, is with lightning strikes creating issues where if there's not conductivity, it can tend lightning can tend to pit a metal. So if you have an actuation system, for example, you don't want that metal to have any surface defects, right, to in fact impair its operation. So they're looking, for example, instead of they'll have seals on these actuation systems, and the seals are help the actuation operate without any contamination from outside. But these seals in general historically have been of non-conductive high performance plastics, and so now many manufacturers are now looking at making these high performance plastics using making them a conductive material, so that way when there's an electronic charge that's going through, it'll pass through that seal and not tend to then impart any pitting that might into that actuation system. So that's just one specific example, but that you could carry that throughout the whole aerospace, not just the airplanes themselves, but other aerospace vehicles that are being designed out there.
So maybe a quick comment still. Oh, go ahead.
Sorry, I was just going to say, if I understand correctly, then it's to make sure you have continuity, you don't have gaps in the conductivity throughout the structure. I do want to kind of pick up on that though with the anti lightning strike protection, because that's an area where we've seen data from some other companies loading a composite with enough graphene material to make it conductive enough to withstand lightning strike protection. And I want to combine this question with another question we've gotten about when you're loading these plastics, whether they be thermosets or thermoplastic resins, the impact on the mechanicals. Now, we've seen graphene added to thermoset resins and to thermoplastics that dramatically improve the mechanical properties. But when you get to a certain load factor, you may have a different impact. What's happening with the mechanicals using your products? And can it reach the level of conductivity to actually impart lightning strike protection that meets FAA and other regulatory requirements?
Okay. I would answer it the following way. I think when we talk about the loadings itself, right? We try to put as much as graphene and fillers and other fillers and components into the resin, right? So make it as high as possible. But again, the goal is to reduce. So normal, graphene level, we're talking 0.5% to 1%, because like also Tim said, there's a certain threshold. When it kicks in, it kicks in. I think what we are able to do is to activate it even earlier. Graphene itself has proven, and we have also test data in SMC and BMC final product applications. So we're not only talking, lab numbers on neat resins compared with some laminates done. So we have really press samples. We have seen impact increase by 28%, right? You have a definite increase in mechanical performance. But again, it's about the design that you add the right components. As an example, for epoxy, it's easier to, one of our focus is the A side. Let me say the bisphenol A side of a system versus the hardening system. There it's easier to bring in because we still stay within the same chemistry. When we talk about an unsaturated polyester, vinyl ester, we have designed a specific carrier resin that has a different chemistry. That's why we want to make as little as possible. So if you would add too much of a different resin, you would have an impact, whether or not you use graphene in the first place, in the amount, because you reduce the original resin. When I've seen in the thermoplastic side, when they go up to filler loadings with especially highly activated active carbon and high-end graphites, etc., to 40 and 50, the question really remains, how much resin is left, right? Where do you get your final mechanical performance? And I think that's where the borderline. Our goal is to reduce the amount of filler, make it more effective with the additive to restore the damages through the process. And the goal is not to add more. Like I said at the very beginning, the goal actually is to improve performance also in conductivity using less. Now, with the lightning piece, I would say we have done some work on helicopter application, etc. There's some data we can share, but there's also, we have some NDA signed with certain end users that we're doing those things. It is a complex system because you really need to look into how the composite is built up in the first place, right? Last word on the carbon fiber that I mentioned before, we also have seen, we're not trying to replace carbon fiber, but we actually have seen the addition of graphene on carbon fiber, and I think there was also a certain webinar within your organization. It's also improving the application of carbon fiber. So there's a significant amount of hydrogen tanks being used with carbon fiber, and if you think about bringing 10 or 20% higher mechanical performance on the already strong carbon fiber into the application might allow us to redesign the tanks and maybe reduce one of 4 tanks to 3 or from 3 to 2 tanks in the car. And it's going to be huge. So there's also significant opportunities in the carbon fiber using graphene with the right binder and sizing, and that's why I mentioned at the beginning, it helps that we also have some glass experience in our working group within the SP2 organization.
Excellent. Let me tag on then to this question about workability. Okay, so there are a couple of questions here. We've answered the question about mechanicals, I think, adequately. The other question comes especially with EMI protection and coating. There are different business factors to take into account. So, for example, what thickness of a coating is needed to achieve the performance? So it's not just the electrical conductivity, but for a given thickness, how much material needs to be added? In the case of adding this to a thermoplastic or even to a resin system, then you have questions about workability, viscosity. People have asked, we've got some questions here about can this work in applications where you have pultrusion? Does it affect that? And then the other question on workability is on cure rate. So, the Graphene Council has done some work looking at EMI shielding as an application. The feedback that we've gotten, and I'd like you to speak about all these things if I can kind of wrap them up, is from the economics, the actual cost of the EMI shielding material is not the major cost. It's the time involved in coating or treating a part, and then how long does it take to cure, which has an impact on the capacity of the businesses that actually apply EMI coatings to it, so that the cost of material is not really always the main determining factor. So just talk to us a little bit about, workability. How long does this stuff take to cure? How does it impact the host material? I think you've already mentioned you don't need special equipment for it. It's used as an additive. But what does it change to the workability and especially the cure rate on a coating and what level of thickness compared to existing EMI shielding solutions?
I don't want to, oversimplify, but this is one of the reasons why we try to use as little as possible, because the less we use, the less impact we have on processability. Obviously, as SP2 Carbon, we started with the field of application that we have the most experience, which is SMC, BMC, open mold, filament winding, pultrusion being an interesting one as well. So we have seen no impact with our additive. You can consider this like a color paste that you add to the system, like a real black color paste, right? There's even some opportunities to move it into a gray area, but it's always going to be between gray and black from a color point of view. Now, the amount that you need, and that's why the design work is so critical and the technical service that we provide is to be able to reduce it to the bare minimum that is necessary. And another reason why I say this is, it's not only the thickness of the coating. It is, I think, the first line of defense behind the coating that you have. It's also if you are able to add, let's say, a surface wheel, and you can imagine you might have a coating, you might have a surface wheel on a barrier coat, whatever you call it, highly filled with our additive and with graphene loading, and a surface wheel to give you mechanical. The laminate behind can be a standard laminate that you always have been using. So our idea is really about designing it where you need it. When you're talking about EMI shielding, you're talking about the surface treatment, right? When you're talking about thermal conductivity, you got to make sure that you have a three-dimensional throughout the laminate distribution of graphene. The way we look at it is we're trying to stay on a carbon content level on the resin system, right? And you still use your fillers, whether it's calcium carbonate, ATH, etc., on the same level that you are used to, because that's the experience you have as an SMC and BMC producer. But we're trying to add 0.5% to maximum 1% of carbon to the final product, which should give us, in the combination with a coating and reinforcement, the shielding that we need. In our view, we try not to use the coating as the only primary EMI shielding protection, although it's the first line of defense, but I think it's a weak line, to be honest. And like you said, it's an additional process. If you look at the battery box, you can coat them, you can put certain foils on it. You may already have shielding performance that you don't even need graphene in the first place, but it's an extra working step. So we want to introduce and leave it in the process that is already industrialized for the SMC, for the BMC guys. And that's the whole purpose. When it comes to curing, there is limited impact, obviously, on a hot cure system, as we talked about pultrusion, SMC, BMC. You got to be careful which peroxide you're using. So you cannot just replace it one by one. You really have somebody to work with that understands the curing system. And I think that's where the bridge is. So on the one hand, I think that's more important for the Graphene Council members is we can help the graphene industry and how to produce and optimize to come to hopefully a good product. But our core expertise is also, and mainly on the downside, having the right formulation, the right design of the resin, and bringing it to the customer, and then go back and say, okay, maybe what can we do on the source of the graphene? Is there something optimized? And that's the bridge where we see each other between the graphene production industry and the composite part manufacturing side. Let me put it this way.
I think that's a very interesting position. Christian, I have just one more question. I do want to answer, though, just to make sure. We have people have asked when we're talking about these percentages of graphene or of the paste, just confirm me, we're talking about percentage by weight, not by volume, correct?
By weight and carbon. So that depends how much carbon graphene as C by weight can we bring into the additive, and then we work backwards to keep it to the minimum level necessary.
Okay, just so we understand the metrics that we're using. We have tons and tons of questions, but we'll have to follow up, I think, with the audience following up on this, and maybe we have a more in-depth article that we can put into our newsletter. But here's a question for you. Do you guys see yourselves as competing with existing EMI shielding solutions, or do you see it more as enabling the ability to bring EMI shielding into applications in a new and novel way, right? If that makes sense, right? Or is it simply a one-to-one replacement? Because there are well-proven EMI shielding solutions. They're at an acceptable cost level. People know them, they trust them. So to be honest, there's not a tremendous motivation for switching in replacing metallics until you get to a certain part. So what is the value prop that really comes in here? Is it because we can design EMI shielding in ways that currently are not being addressed, or is it because this is a better way of doing it and getting metallics out of the systems?
Well, I was just going to say, I think you're trying to improve things, right? So if you're saying, yeah, are we just going to replace an existing product that's out there and just to give it equal performance? I mean, if somebody wanted to do that, but there has to be a value. So I think that's where we come in hand, where we're providing a value is saying, hey, we can help you formulate, we can help you design a system, that will optimize the performance. And so whatever that may be, and there's always a compromise, right? So if you can reduce the amount of graphene, well, maybe you don't want to. Maybe you want to have it at a specific level for specific reasons, for physical performance, whatever. Or another filler. You could use another filler by loading, by having a little more flexibility in the design based by using our paste. And the paste was specifically made so that it's compatible with the system, and then gives you the flexibility now to, okay, let's see what we can do to make it better. And I think, Christian, you can go ahead and talk from here, but that's the technical service part that we provide as well.
The only thing for me to add is that what we do is we don't put any new EMI shielding technology on the market. What we do is, given the 30 years of also network and contacts we have, we also explain the OEM, whether it's in the car, in the automotive industry, or in the aerospace, or in the boat industry, or coming from the pultrusion side, what's possible. And it's their product that we optimize. If they say, look, maybe I want to produce with my part for the application I have, whether it's a pipe or other things. Gas pipes, for instance, is a very, very interesting application. We don't produce the pipe, right? But we help the gas pipe producer to maybe replace the carbon wheel they're using, optimize the resin system together with the reinforcement to make it an anti-static performance. So it's not the application that we're reinventing. We're helping the OEM to understand what's necessary. And then the guy who's actually doing it, the compounders and the tier 1 or tier 2, to bring that graphene whenever, it's going to be a business case that makes sense, right? To replace something, or in an ideal world, to do something new. At the end, it's weight reduction wherever possible. I think that's where we're aiming for.
If I can, just our observational point as the Graphene Council, because we see all these different technologies come together, it seems where you guys sit is this nexus of you need EMI shielding, you can get and leverage graphene for mechanical performance, and that also results in light weighting, which feeds into what's needed now especially for the transportation industry and the electrification of transportation. And the other point that should not be lost on anybody here is, graphene is just not one of those materials anybody can take a bucket of it, chuck it in, and it'll work. You do need to treat it as a specialty chemical that needs to be tuned to the host matrix and the properties that you want to get. And it sounds like that's really what you guys bring to the table, is that formulation experience plus the demonstrated testing that you've had for this material to optimize, meaning use as little as you need to get the performance you want to achieve. Does that sound correct?
Sounds perfectly fine.
Yep.
With maybe the addition, if you allow, there is a certain, out of our experience, global platform that you need. So as an example, whether it's the batteries or whether it's electronics, right? Europe is not a big market in terms of production, but there's still going to be a lot of development opportunities there wherever it's rolled out globally. So and that's why we have this global platform, is as well to provide the OEM and companies to the OEM with maybe a development work in Europe that is going to be produced in China only, right? Or also help the Chinese guys to get on the market, even with a European OEM, because there's also a trend. There will be development for the Chinese market, let's say Audi or others, in China for China, right? And you can stay within our platform and we can cross-reference and we basically transfer those things. And I would invite also anybody who is having challenges with their graphene to come into the composite world, whether or not it is the processing in the composite that is actually impacting the performance of the graphene they already have, because they provide all this value, and sometimes it's like a 50% chance it's working or it's not working. And what's missing is maybe some of the ideas to redesign and redrive and maybe change a few things, very little things. That's why it's coming in handy that we also have our own graphene production, right? But obviously this is not a one-stop only. We are, as SP2, looking into all the different combinations, and I think we're in an interesting spot. But again, being a small organization, we really have to prioritize, because like you also know, Terence, the field of potentials is huge. You know, we have not even talked about concrete or anything. And there was a very interesting webinar on this as well. So we really stay in the composite world because that's the experience. And even within that world, there's still enough of opportunities out there.
Excellent. Well, we look forward to seeing you and a whole bunch of people at ChemX coming up soon in a couple of weeks, where we can go head deep into the composites world. There are tremendous opportunities. Composites itself as a sector is growing rapidly because of its applications, and graphene type applications just make composites better. So I think that's a great opportunity for all of us. And with that, Tim, I want to thank you very much for your time in the presentation, and Christian, for you and your whole team for sharing with us today. And with that, I think we'll conclude today's webinar, and want to thank everybody for joining us today. Thank you for being a participant in the webinar with the Graphene Council. And if you have questions, anything graphene related, you can feel free to contact us. And we encourage you to reach out to SP2 Carbon if you have questions about the technology that you heard about today. With that, thank you all very much. Have a great day.
Thank you for the opportunity.
Thanks, everybody. We look forward to working with you.